In the last lecture, we looked at the electric field lines, non-uniform electric field, and uniform electric field. In this lecture, let's look at a numerical example of motion in a uniform field. An electron with an initial speed, Vi, that equals to 1.6 times 10 to the power of 6 meter per second, enters into the electric field midway between the parallel plates shown. So we have a parallel plate, we have positive on top and negative on the bottom. So the electric field is pointing downward, and we place this electron midway between the parallel plate. And we are going to assume that the field outside the plate is 0 and ignore the gravity. The plate is separated by 1 centimeters, so the midpoint will be 0.5 from each of the plate, and the length of the plate is 2 centimeters. In part A, if the electron just misses the upper plate as it emerges from the field, find the magnitude of the electric field. Then we have to justify whether it is valid to ignore the gravity. Then in part B, let's find the speed of the electron as it emerges from the field. Then in part C, the electron is replaced by a proton with the same initial speed. Will the proton hit one of the plates? If not, what would be the magnitude and direction of its displacement as it exits the region between the plates? Here I have the sketch. The two plates are separated by 1 centimeters, and we place an electron in midpoint of the plates. We have uniform electric field that is pointing downward, and the electron has an initial speed of 1.6 times 10 to the power of 6 meter per second. In part A, we want to find the magnitude of the electric field, such that the electron just misses the upper plate. So when we have uniform electric field, then the acceleration is constant, so we can use the kinematic equations. First of all, the force on the electron, it equals the charge times the uniform electric field. The charge is negative E, since it is an electron, and the electric field is pointing downward, so it equals to negative E, the magnitude, times J hat. We cancel out the negative signs, so the force is upward, E times the electric field, J hat. And from Newton's second law, since we are ignoring the gravity force, so the only force acting on the electron is the electric force. So net force equals to mass times acceleration. We isolate for the acceleration. We get net force divided by the mass. The net force here, we just found that it equals to E times electric field, since electric force is the only force. So E times the magnitude of the electric field divided by mass of the electron. And it is pointing in the J hat direction. Let's call this equation 1. Here we have constant acceleration, so we can use the kinematic equation. Let's look at the x component. Let's use this equation. Delta x equals initial velocity in x, which is v0 from the sketch, times delta t, then plus half of the acceleration in x times delta t squared. But since the acceleration is in the j hat direction, so ax is 0. Then we get delta t, we isolate for delta t, which equals to delta x divided by v0. And let's call this equation 2. Now let's look at the y component. We use the same equation. Delta y equals initial speed in y times delta t plus half of the acceleration in y times delta t squared. The initial velocity in y is 0, so this is 0. Then we can substitute the acceleration from equation 1 and the delta t from equation 2 into this equation. We sub 1 and 2. So this equals half times the acceleration in y, which is E times the electric field divided by mass of the electron, times delta t squared. Delta t is delta x divided by initial speed squared. We have delta y, which is 0.5 centimeters. Delta x is the length of the plate, which is 2 centimeters. We have the initial speed, v0. We have the mass of the electron, and E is the constant. So then we can isolate for the electric field to find its magnitude. So E equals 2 times delta y times mass of the electron divided by E times initial speed divided by delta x squared. Then we substitute the numbers. 2 times delta y is 0.5 centimeters, which is 5 times 10 to the power of negative 3 meters. Mass of the electron is 9.11 times 10 to the power of negative 31 kilograms, divided by E, which is 1.6 times 10 to the power of negative 19 coulombs. Then, initial speed is 1.6 times 10 to the power of 6 meter per second, and delta x is length of the plate, which is 2 centimeters. In meters, it is 2 times 10 to the power of negative 3, and this square. We substitute the numbers, and we get the magnitude of E equals 364.4, unit is newtons divided by coulombs. And we also want to justify whether it is valid to ignore the gravity. So let's compare the gravity force to the electric force. The magnitude of the electric field is magnitude of Q times the electric field. We just found that the electric field is 364.4. So we substitute the numbers. We get 6 times 10 to the power of negative 17 newtons. And the gravity force, its magnitude is mass of the electron times G, 9.8. And we get 9 times 10 to the power of negative 30. So we found that the gravity force is a lot smaller than the electric force. So we just justify that it is okay to ignore the gravity force, since its magnitude is a lot smaller compared to the electric force. And in part B, we want to find the speed of the electron when it hits the upper plate. When it hits the upper plate, it has the x component and the y component. So we have to find both. For the x component, the final speed. Since there's no acceleration in the x direction, so the final speed equals to the initial speed, which is v0. That is 1.6 times 10 to the power of 6 meter per second. And the final speed in y, we can use the kinematic equation. Initial speed in y plus the acceleration in y times delta t. Initial speed in y is 0, so the final speed will be acceleration times delta t. Again, we can substitute equation 1 and equation 2, which equals acceleration is E times the electric field divided by mass of electron, and delta t is delta x divided by initial speed. Then we substitute the numbers. E is 1.6 times 10 to the power of negative 19. And we just found the electric field. Its magnitude is 364.4. Then divided by mass of the electron, which is 9.11 times 10 to the power of negative 31 kilograms. Delta x is length of the plate, which is 2 times 10 to the power of negative 3 meters. And initial speed is 1.6 times 10 to the power of 6 meter per second. So the final speed, we use Pythagoras theorem. It would be the square root of the sum of the squares, bfx squared plus bfy squared, which equals to 1.79 times 10 to the power of 6 meter per second. And in part C, we replace the electron by a proton. We want to find whether the proton will also hit the upper plate. If not, what is the displacement as the proton exits the region? Let's also start from the force acting on the proton. It equals to charge of the proton times the electric field. Charge of the proton is positive E, and the electric field is uniform, pointing downward, so negative the magnitude of the field, J hat, which equals to negative E times the electric field times J hat. And same thing, using Newton's second law, we get the acceleration on the proton would be the net force on P divided by mass of P, the proton. And we're ignoring the gravity force again. So the net force equals to the electric force, which is negative E times the electric field divided by mass of proton in the J hat direction. But since the mass of the proton is a lot greater than the mass of electron, and from the equation of the acceleration, the mass is in the denominator. So acceleration of the proton would be a lot smaller than acceleration of the electron. So the vertical displacement is not going to be as large as the vertical displacement of the electron. So when the proton exits the region, it's not going to hit the plate. Let's find the delta y that is going to travel. We use the kinematic equation again. It is half of the acceleration in y times delta t squared. And here the delta t is same as before. So delta y equals half of the acceleration, which is negative E times the electric field divided by mass of proton times delta t squared. Delta t is delta x divided by initial speed. We substitute the numbers. We get negative half times E, which is 1.6 times 10 to the power of negative 19. And the magnitude of electric field is 364.4 divided by mass of proton, which is 1.67 times 10 to the power of negative 27. Then times delta x. The delta x is still the length of the plate, which is 2 times 10 to the power of negative 3 meters. And vi, initial speed, is 1.6 times 10 to the power of 6 meter per second. And this square. And we get delta y is negative 2.7 times 10 to the power of negative 6 meters, which is negative 2.7 micrometers. So this is a lot smaller than half of the distance of the plates. Half of distance was 0.5 centimeters. But now the proton only traveled 2.7 micrometers. And the reason why the electron and proton travel different displacement is because the mass of proton is a lot greater than the mass of electron. So its acceleration would be a lot smaller than acceleration of the electron. And that is the end of the lecture. So far we talked about the electric field due to point charges. Starting from the next lecture, we are going to talk about the electric field due to charged bodies.